Okay, so our previous video was working when the standard deviation was known. This one we're going to work when it's not known. Because it's not known, we're going to work with a t, have to work with a t. If it were known, we could work with a normal. And real quickly with the normal, we know that with a normal, we can kind of use the empirical rule and go plus or minus 1 standard deviation, 68%, plus or minus 2 is 95%, plus or minus 3 is 99.7%. However, with a t distribution, there's a different distribution, or there's a different percentage between standard deviations for every single sample size. So it's going to change for every single degree of freedom or for every single sample size. And remember, degree of freedom is just n minus 1. So we're going to keep the same sample mean as we had in the previous video, which was 77. The same sample standard deviation is 12.5. And our same sample size of 25. So our standard deviation is going to be the sample standard deviation of the x bars is this s divided by the square root of n. So in this case, it's still going to be 12.5 divided by the square root of 25, which is 2.5. So that's not going to change. We're going to keep that the same. All right. And, but we need to figure out a couple things. So our formula is going to be x bar plus or minus t star s divided by square root of n. That's going to be our formula. And our t star is associated with our confidence level. And we're going to make 68% confidence levels, 95% confidence levels, at 99.7. Well, like I said, with a z, if we're working with a normal, that's going to be an easy t star for 68% would be 1, t star for 95% would be 2, t star for 99.7 would be 3. But it's going to vary. It's not going to be 1, 2, and 3 for a t, since that would have been for a z. This is going to be for a t. So we're going to need to calculate that. We're going to have to drop down our sheet just a little bit. And we're going to go to a place on a calculator, second vars, and we're going to use inverse t and 1 minus our confidence level divided by 2. All right. And our degrees of freedom are going to be n minus 1, which in this case is going to be 25 minus 1, which will equal 24. So let's do that real quickly and let's calculate some t stars. So second vars, inverse t, parenthesis, 1 minus, we'll do the 68% first, divided by 2, degrees of freedom, 25 minus 1. And we end up getting 1.015, and that's going to be a plus or minus 1.015, and that's where this value came from. So between here and here lies 68% of my data will be between. And notice that's slightly larger than the z-score. Why? Because there's more area in the tail, so we have to be a little further spread out. It's a little, the t distribution is a little more spread out. There's more variation. So instead of being 1 standard deviation, we're 1.01 standard deviations. Okay. To go to 95%, we're going to go back and do the same thing. Second vars, inverse t, and it's going to be parenthesis 1 minus 0.95, close parenthesis, divided by 2. And we end up getting 2.064, and I rounded just because I don't want to carry out all the decimal places. And then I'm going to do the same thing, second vars, inverse t, parenthesis 1 minus 0.997, close parenthesis, divided by 2, degrees of freedom 24. And we end up getting about 3.302. All right. And notice I have basically my formula. My x bar was 77 minus 3.032 times my standard deviation of my sample divided by the square root of n. So I end up getting a lower bound for 99.7, or about, if I calculated this out, we'd get 68.75 to 85.25. 71.84 to 82.16, and 74.46 to 79.54 would be, this is 68%, this is 95%, and this is at 99.7%. Well, this would be a whole lot of multiplication, and yes, this is the type of work we would need to show, but the calculator is actually very, very friendly on this. So let me show you how to do this on the calculator, where it'll give you our upper, lower, and lower bounds. So we're going to go stat, test, number 8 for t interval. Our mean is 77. Our standard deviation is 12.5. Our sample size is 25, and our confidence level is 0.68. And I press enter, and I get a lower bound of 74.46 and an upper bound of 79.53, and 68% of my data is going to be there for this particular t distribution that had a n equal to 25. So our degrees of freedom is 24. Stat, test, and we want to do the same thing for 95%. So stat, test, t interval. Mean sample, a mean of 77, 12.5 in this, our confidence level is 0.95. When we do that, we're basically saying that we're 95% sure, 95% confident that the true population mean falls between 71.84 and 82.16. Our best single estimate is 77. That's our best estimate. The sample mean is always our best estimate. But we are saying, you know what? We're 95% confident. We know that our samples could vary, and we're 95% confident it lies within this interval. And then we can come back and go stat, test, and go to number 8, t interval, 0.997. And in this case, we're 99.7% sure that it lies between 68.7 and 85.25. And that's how you would calculate roughly a confidence interval for a t distribution. Please remember, the t distribution, the standard deviation of the population is not known. The other thing is we need to know that the underlying distribution is normal, or that our sample size was 30. All right, I hope that helped. Thank you for watching.